different substances. Now, covalent bonds are created between non-metals. And so as we look at basically the non-metals in the periodic table, we have carbon, nitrogen, oxygen, phosphorus, sulfur, selenium, and hydrogen. What we're going to look at is how many bonding sites each one of these has. And so if we look at carbon, carbon has 4 valence electrons. And so carbon's going to have a Lewis structure that looks something like this. If we look at nitrogen, there's going to be 5 valence electrons, which means that 2 of the electrons are paired up while the other 3 are alone. So we have 3 bonding sites. And oxygen, we have 6 valence electrons, so we have this structure where we have 2 pairs and 2 alone electrons. And then last but not least, we have 7 valence electrons in the last one. And as we draw it, that means if we look at all these different elements and we look at those different columns, that the column with carbon in it actually has 4 valence electrons. So I always look at it as saying that it has 4 bonding sites. Nitrogen has 3, oxygen has 2, and fluorine has 1. And so now, by knowing that information, we can start to put together some interesting compounds. So if we start just thinking about carbon, carbon's going to have 4 bonding sites. And in the last video, we brought hydrogen in, and we said, hey, let's bond hydrogen to this thing. And so we came in and said, okay, so here's one hydrogen, here's another hydrogen. But we can also do some other things. Notice that fluorine has 7 valence electrons. So what we can do is we can actually add in fluorine and bond it into this compound too. And so if I take a fluorine here, there's 7 valence electrons, and then put another fluorine down here. And so what we're doing is looking at satisfying this octet of carbon. If you look at it, 2, 4, 6, 8 around carbon, and this fluorine also has 2, 4, 6, 8, and this fluorine has 8. Hydrogen, again, if you remember, is in the first energy level, so it only wants 2. And so we have a compound like this. If we look at something like what's called methanol, and by the way, meth in carbon, when we start talking organic chemistry, meth means 1 carbon. So if we do CH3OH, and we start to look at all the compounds, or all the Lewis structures, carbon's going to have 4 valence electrons, as always. Okay, so we draw that out. And if we add hydrogen in here, we're going to pop some hydrogens on. There's a hydrogen. There's a hydrogen. So there's our CH3. And now we just need this little OH to be sticking off the end. And so if we take oxygen, notice oxygen will come in here, and there's our bond, our pair of electrons. And then we have these other 5 electrons that we have to consider. And then last but not least, we have this final hydrogen. And we bond it off the end. And you notice that we've satisfied the 8 for carbon and oxygen. We've satisfied the 2 for each of the hydrogens. And so as we start to explore this, we're going to look for satisfying this 8. That's not always the case, though, because there are some situations where we can go beyond or extend the octet rule. And that's what we're going to do on this next slide. If we look at the typical Lewis dot structures, you'll notice we have SF2, SF4, SF6. We also have to consider that sulfur, if you look at the valence shell of sulfur, it's in the 3s, and it has 2 electrons like this. And then we have the 3p. There are 2 bonding sites. So you can see those 2. And if we took 1 electron from, say, the fluorine, what's going to happen is that electron from fluorine is going to come in. One of them is going to come in there, and the other one's going to come in there. So we satisfy this octet of sulfur again, and I'll draw this guy over here so that we can have, so we do sulfur, 1, 2, 3, 4, 5, 6. We'll come back and put the fluorines in there. There's that electron that's facing down right there. Okay, and we finish out our 7. And then we put our second fluorine, which is going to be that electron, and we're going to finish out our 7 there too. And now we have that SF2. In the third energy level, though, let's erase this and we'll give us some room to work. In the third energy level of sulfur, well, in the third energy level of any atom, there are available d orbitals that are not occupied. So what we're going to do is we're going to draw these d orbitals unoccupied. So we got 1, 2, 3, 4, 4, 5. So we got 3d. And notice there's no electrons there. For sulfur to be able to bond to 4 things, or even 6 things, what we have to be able to do is take a paired set of electrons and separate them. Well, for that to happen, we actually have to take this pair of electrons right there. We're going to take one of those electrons, and we're going to take that electron and we're going to move it. We're going to take that one and we're going to move it up here to the D. And so if we do a little erasing, I'm going to go in and erase some things. Oops, that's just writing again. Let's put that electron there and then we'll erase. Okay, we're going to get that out of there. Now, notice as soon as I moved it there, how many available orbitals are there to actually start to bond? Now we have 1, 2, 3, 4 spots that are available to bond. And so as we start to add these things up, now I have these 4 spots around sulfur to bond, and we come in with our fluorines and bond them to each one of those sites. So there's 1, here's 2, there's 3, and last but not least, we get this 4th one down here. This violates the octet rules, because if you start counting electrons all the way around the sulfur, you got this pair down here, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So sulfur actually is seeing 10 electrons as opposed to just 8. And it's because of the d orbitals that this can be allowed. If we go to SF6, we kind of have to do the same thing, except we're going to go grab this particular electron and move it. So I'm going to draw him out there. Well, we put that electron out there and we're going to go erase it. And you'll notice that we're going to end up with 6 bonding sites, or 6 unpaired electrons now, which allows us for 6 different bonding sites. Okay. In phosphorus, as we look at the chemical below this, it works basically the same way. So what we're going to do is, first of all, it should be, and I'm just going to draw lines here. There's 1, 2, 3, 4, 5. So there's just 5 valence electrons. We can bond to chlorine here. Okay. We bond to another chlorine. And remember, a line represents 2 electrons. And we bond to another chlorine. And that works fine. That's what it should be. You notice 8 electrons around it. But here we have PCl5. So again, we're going to go in and we're going to separate a pair of electrons. If you think about this drawing up here, we're going to separate those 2 electrons. And so when we redraw this, we're going to have those 2 separated. Plus, we have all these other single electrons. And now we can bond to chlorine all the way around. And we put all of our electrons on chlorine. And this gives us what we call the extended octet rule. This can only happen if the central atom has a d orbitals. Besides that, you're not able to do that. Okay, that's the end of the extended octet for d orbital, or using d orbitals and the Lewis structures.